Conjugate roots of polynomials. Here's the theorem. If a polynomial of degree more than 2 with real coefficients has a complex root z, then its conjugate z star is also a root. In other words, complex roots with polynomials with real coefficients occur in conjugate pairs. So for example, right, if say the number 2 plus I is a root, okay, then you automatically know that 2 minus I is also a root. Now, okay, so now let's study why this theorem is true. So let's call this polynomial f of x, okay, and since it is a polynomial with degree more than 2, I can say that, well, I could call it, say, a0 x to the power of 0 plus a1 x to the power of 1 plus a2x squared, okay, all the way until, say, an minus 1 x to the power of n minus 1 plus an x to the power of n. Okay, the degree, right, n is more than 2. Okay, and I also know that a0, a1 until an are all real numbers. So now I'm told that this polynomial has a complex root, okay, z. So if z is a root, okay, then I would know that f of z equals to 0. Okay, that's by factor theorem. So this means that, well, a0z to the power of 0 plus a1z to the power of 1 plus a2z squared until an minus 1 z to the power of n minus 1 plus an z to the power of n, the whole thing is equal to 0. Okay, now, but we want to show now that when this happens, its conjugate z star is also a root. Okay, and this is the same as saying that we need to show that f of z star is equals to 0. Okay, so now let's see what is f of z star. Okay, so f of z star is equals to a naught z star to the power of 0 plus a1 z star to the power of 1 plus a2 z star square added until an minus 1 z star to the power of n minus 1 plus an z star to the power of n. Okay, and the question now is this equals to 0? Okay, we don't know. So how are we going to observe this? Well, okay, maybe if I can somehow transform this equation, okay, into this equation, because if you stare at both of them, you know, they really look alike. The only difference is that a z, you know, becomes a z star, okay, throughout. And if I can do something to this equation, okay, maybe I would be able to conclude something about this expression, okay, on the left-hand side. So maybe I could take the conjugate of everything on the blue equation over here, okay? Because when I take the conjugate on the blue equation on the left-hand side, I will get this left-hand side over here. Now, why is that so? Okay, because if you recall, right, if you recall what we've done in class, if you recall that, well, actually, z star to the power of n is equals to zn star. Okay, so if we take, you know, conjugates throughout on the left hand side, we will be able to swap the star and the power, okay, and we will be able to see, you know, all these terms, you know, emerging. Okay, I'll show you later. But more than that, okay, also, if you take a real number, say a, all right, and you take its conjugate, actually nothing happens to it, right? It just remains the same, okay, for any real number a. Okay, and that is really why it's important to take note that all these numbers are actually real numbers. The coefficients, okay, are real numbers. okay, so that we don't end up getting more complicated calculations. Okay, so let's do that. Okay, let's do this now. So we start with f of z, okay, equals to 0, and that is the same as saying that a naught z to the power of 0 plus a1 z to the power of 1 plus a2 z squared added up until a n minus 1 z to the power of n minus 1 plus a n z to the power of n equals to 0. Okay, and noting that a0, a1 until an are all real numbers. So now let's take the conjugate on both sides of this equation. Okay, so when I take the conjugate throughout, okay, I can kind of distribute the conjugation. So I'll get a0, z0 conjugate plus a1z to the power of 1 conjugate plus a2 z2 conjugate, okay, plus an minus 1 z to the power of n minus 1 conjugate plus an z to the power of n conjugate equals to 0 conjugate, which is just 0. Okay, now the reason for this, all right, if you recall the properties, all right, if you have z1 plus z2 conjugate, it is the same as z1 conjugate plus z2 conjugate. Okay, so now term by term, we're going to apply the conjugate into the expression, because z1, z2 conjugate is equals to z1 conjugate times z2 conjugate. Okay, refer to the properties of conjugates if you're not sure. Okay, so on each term I'm going to apply that. So this would give me, okay, this would give me a0 conjugate z0 conjugate plus a1 conjugate z to the power of 1 conjugate plus a2 conjugate z square conjugate added until a n minus 1 conjugate z to the power of n minus 1 conjugate plus a n conjugate z to the power of n conjugate, and the whole thing equals to 0. Okay, so but a conjugate is just a naught, okay, because they were all real numbers, if you remember. Okay, we were saying earlier that a conjugate is equals to a for all real numbers, a, and that's actually why 0 conjugate is just the same as 0. So this a naught conjugate is equals to a naught, right? And z naught to the power conjugate is z conjugate to the power of 0 plus a1, which is the same, times z conjugate to the power of 1, okay, plus a2, nothing changed, z conjugate square, okay, a n minus 1, z conjugate n minus 1 plus a n z conjugate to the power of n equals to 0. Okay, this step is because, well, z to the power of n conjugate is equals to z conjugate to the power of n. Okay, it's actually sort of linked to this one. Okay, it kind of says the same thing. Okay, so now look at this statement over here. This is the same as saying that f of z star is equals to 0. And that means that z star is a root of f of x, the polynomial.